Hello, and welcome to a lecture on radiation from an electric current element. My name is Steve Ellingson. In this lecture, we'll be talking about how to compute the radiation, the electric and magnetic fields from an electric current element, a very specific current distribution. And along the way, we'll discuss some of the implications of that derivation, including the Farfield conditions, and a simpler way to compute the electric and magnetic fields once you realize the implications of the Farfield condition. The outline of this talk is as follows. First, the problem statement. Then I'll remind you about how to find the electric and magnetic fields from a general current distribution, and this is the most general formulation, which we'll quickly narrow down. How to compute the electric and magnetic fields for an electrically short electric current element. That's a mouthful, so I'll usually abbreviate that as ES-ECE, where ES is electrically short. We'll do two cases here, in fact, the electrically short current element and the not necessarily electrically short electric current element. Then a discussion of the Farfield condition, which emerges as part of this work. And then, as promised, a simpler way to get the electric and magnetic fields from a current distribution, the far field. And now we'll be talking about general current distributions. Okay, here's the problem statement. I have a filament of electric current. It's flowing upward. In other words, the direction of current flow is as indicated by the arrow. And the length of this current filament is given as delta Z. Now, I've drawn this in the Cartesian coordinate system. There's really no reason why this current couldn't be oriented in some other direction. The choice of Z is completely arbitrary. So realize that we're doing this without loss of generality. And in fact, when we get to the end of the lecture, I'll show you a simple exercise where you can exercise that idea. Now, initially, we'll say that the current is electrically short. And by that, we mean that delta Z is much, much less than a wavelength. Now, how much less than a wavelength? That depends. Certainly, 1/100th of a wavelength would fit the bill. Perhaps 1/10th of a wavelength would also be okay. Delta Z equal to a wavelength is clearly not okay. So what satisfies this condition depends on the application. I'll remind you the general technique for getting the electric and magnetic fields from a current distribution. And it goes like this. First, you integrate over the currents to get the magnetic vector potential, A. Then you use the defining relationship for A to get H. That is, the curl of A divided by mu gives you H. And then you can use Maxwell's equations to get E from H. So if we apply that problem here, on the left we see the problem statement. On the right we see the general expression for the magnetic vector potential. So the first step in this solution. We need a expression for the current distribution in this case. And the appropriate one is to rewrite the product of the electric current density, which remember has units of amps per meter squared, times the differential volume element, which remember has units of meters cubed, and to rewrite this now as a vector. The current's going in the z hat direction, so we give it the z hat unit vector. A current, which has units of amps, and a differential length, which has units of meters. And note that the units on both sides are the same. That is amps times meters on the right, amps times meters on the left. And perhaps you know that this is referred to as a current moment. So I make that substitution. The new form of, or the specific form of the radiation integral now looks like this, where I have now identified the endpoints. I'll be integrating from minus delta Z over 2 to plus delta Z over 2 of this specific formulation. And I've also replaced now R prime with the specific description of what R prime is, that is Z prime Z hat. So various positions along the current element as I integrate. So r prime is the thing that's changing. And in fact, in general, when I use this prime notation, I usually use prime to indicate things which are changing as with the variable of integration. So now we simplify the radiation integral. The original radiation integral is certainly solvable, certainly numerically solvable, but we're looking for simpler expressions that are as good. So here's the idea. First, what is formally true? Well, here is the position to the source point, r prime, and then here is the field point out here, which we just call r. And what we need in the integral is r minus r prime. That's what shows up in both the phase factor and in the magnitude factor. So what we'd like to do is simplify this a bit. And the way we do that is we take the phase factor, here it is identified here, we take the magnitude factor, identified here, and we apply some approximations that emerge because this is electrically short. So because this is electrically short, we can make these assumptions. First, since the distance to the field point will be assumed to be much, much greater than the length, and also because delta z is assumed to be much, much less than a wavelength, that's the electrically short part, we can simplify the phase factor to simply be e to the minus jk r. That is this distance here. And the reason we can do that is because the maximum variation that we expect to see here is always very, very small, and specifically very small compared to 2 pi. So if this whole thing varies by amount much, much less than 2 pi, then the whole phase factor really doesn't change very much. Okay, and on the bottom, we have the magnitude factor. Now, again, because we'll assume the field point is the distance to the field point is much, much greater than the length of the current element, this part makes very little difference, and so we replace that with the magnitude of r. So the new phase factor is this thing. So this applies when it's electrically short, and also when the distance to the field point is much, much greater than the length of the element. So here's the radiation integral we came up with a few slides back. Now we apply the approximation that we came up with. So now the phase factor times the magnitude factor is now replaced with this simpler form. We can pull out the constants, and the constants include the phase factor and the magnitude factor, because now neither one of those two things is varying as a function of the variable of integration. We're left with integration over just length, so this is a very simple problem. We now find that the magnetic vector potential is simply z hat, mu over 4 pi, the current moment here, times the phase factor, times the magnitude factor. So we get a surprisingly simple result. And remember, when the source is a current moment, the magnetic vector potential always points in the same direction as the current moment. So this makes sense. Okay, next we get the magnetic field intensity from the magnetic vector potential. At the top here, I start off with the result from the previous slide. I take the curl of that expression and divide by mu. So I pull out the constants, the things that don't vary with respect to space, and I'm left with taking the curl of this thing. It's a relatively simple thing to do, but you should verify it on your own. The result looks like this. So I get phi hat, a factor of sine theta, the current moment divided by 4 pi, and then here's some magnitude factors, one that goes as 1 over r, another one that goes as 1 over r squared, and then the phase factor. So right away you can see that this looks like a spherical wave. This is e to the minus jkr, that's a phase front which is constant over a spherical surface surrounding the current moment. And then we see 1 over r here, so that's like a simple spherical wave. But we also see this 1 over r squared dependence, which kind of muddies the water a little bit. This solution for the magnetic vector potential is a bit more complex than what is needed for most antenna work. Just to give you a quick preview here, it's because this term really doesn't matter that much if I get far enough away from the current moment. So we can simplify this, and we do it as follows. I take that expression, jk over r plus 1 over r squared. I multiply the top and bottom by r, so this gives me jkr over r squared plus 1 over r squared. Now I note the following things. If we also assume the field point is electrically far from the source, and that's what we've been doing all along, I can rewrite this as r over lambda is much, much greater than 1. And if that's true, then 2 pi over lambda times r is also much, much greater than 1. And 2 pi over lambda is just k, the wave number. So this is the same as saying that kr is much, much greater than 1. If I apply that idea now, then I see that this factor here makes relatively little difference. And this first factor now must dominate. So I get jkr over r squared, and I get an r cancels, some cancellation in r here, so I end up with jk over r. So this expression really just simplifies to the first term, and as I claimed to before, the second term doesn't really matter that much, as long as I'm electrically far from the source. Okay, now I've got h. I've simplified it using the approximation identified in the previous slide. To get E, I take the curl of H. Now, just keep in mind, this is the second time we've had to take the curl. So this is getting a little bit onerous mathematically. Here's the expression, the appropriate Maxwell's equation that gives us E from H in general. Here's the resulting expression. We get theta hat. E is in the theta hat direction. We get this factor of sine theta again. We get the current moment divided by 4 pi again. We get a factor of j omega mu divided by 1 over r and e to the minus jkr. Also a spherical wave now. And again, you should verify this step on your own. I'm omitting here all the details of the curl, but it's relatively straightforward mathematics. It's just a little bit tedious. Okay, so let's summarize what we have so far. On the left is the problem statement. Delta z, remember, is electrically short, so it's much, much less than a wavelength. We're assuming that we have field points, which are in the far field. And if we do those things, then we find that to a very good approximation, the electric and magnetic fields look like this. Now, let's just take a moment to consider what these fields look like. E is always theta hat directed. So here is E at various points in space, because that's the theta hat vector. H is always phi hat directed. So phi hat goes like this, goes like this. If I show it next to one of the theta vectors I've already shown, it looks like this. So this is the orientation of the electric and magnetic fields. And in fact, you could have anticipated that from very simple undergraduate electromagnetics. The sine theta factor contributes a pattern factor. If I draw the magnitude of the fields now, we see that when theta is equal to 0, that's this direction, I get a null because sine theta is 0 in that direction. And sine theta is a maximum in that direction because theta is pi over 2 in that direction. So we get this thing that looks like a donut. That donut now represents the magnitude variation of the electromagnetic fields as a function of theta. The color scheme here means nothing, by the way. I'm sure it's just here to make the picture look pretty. We can check this solution. One of the ways we check the solution is we know that the ratio of E to H in general should be equal to the intrinsic impedance of the medium, also known as the wave impedance. If we do that here, we can take the ratio of the magnitude of E to H. Here I substitute the expressions that we obtained. You very quickly find that this is omega mu divided by k. I can replace k with its expression in terms of the constitutive parameters. I get this, and this quickly reduces to the square root of mu over epsilon, which is the intrinsic impedance of the medium as expected. Okay. Now let's consider what happens when we have a non-electrically short current element. So everything's the same here, except for two things. First, we have this length L, and L is not necessarily less, much less than a wavelength. The second thing that can happen is that the current density can vary over the current element. So what we're going to do now is we're going to say that the combination, the product of the current density, again, amps per meter squared, times the volumetric differential current element, meters cubed, is now given by a unit vector, z hat. That doesn't change. But now the current can vary as a function of z prime. That has units of amps. And again, z prime here, that has units of meters. So it's dimensionally correct. And what has changed now is that the current is no longer uniform over the length of the element. Now, we don't have to say what it is specifically, but you probably know already that in a practical thing, like an antenna, if this was an antenna, the current here would have to be 0, and the current at this endpoint would have to be 0. And so we would have some constraints so that, for example, a small element of current would have a current distribution that might look like this. If it was slightly longer, it might look like this, and so on. We're not really concerned about those details here. I just thought I'd point that out to make the connection to actual antennas. For the moment, we can just say I is some function that we don't have to identify yet. Okay, the way we solve this problem now is we exploit the previous solution that we had for electrically short electric current elements. What we can do is take this longer current element now and break it up into these little chunks. But now we can arrange them in space and then add them up. So that's the idea. Each chunk is located at a source point, r sub n. The distance from the source point to the field point is given by r minus r sub n. And then I take each one of these solutions and I add them up. So I have n, big N chunks, and I just add them up for each point in space. And here's the result written out now, the sum over n chunks. And then I'm just taking the solution I came up with previously and generalizing it, because now I have not chunks at the origin, but now chunks located at different points along the z-axis. And then I'm also pointing out that I have to take into account where I am when computing the current density. So here's the expression from the previous slide. I'm going to let Zn go to Z prime, and I'm going to let delta Z go to delta Z prime. You probably see where this is going. I can turn this into an integral. Right, so now I don't have to think of these as chunks. I can just think of the chunks as becoming differential contributions to the answer, and I can turn it into an integral. This integral has endpoints, which are plus and minus L over 2, and that's really all there is to that. But now we want to simplify the integrand as we did in the electrically short case. This time, however, we have to be a little bit more careful with the phase dependence. So this is our new phase factor and magnitude factor. They look like this. Previously, we assumed really three things. We said that the field point, the distance to the field point was much, much greater than the length of the current element, and we're still going to assume that. And we're saying the same thing here. And here, we can no longer make this assumption. We can no longer say that the length of the current element is much, much less than the wavelength, because we're saying that we're no longer electrically short, at least not necessarily. So the magnitude factor can be simplified as it was before, but the phase factor really can't. Oh, by the way, that beta should be k. Sorry about that. So I have to figure out now what to do with the phase factor. Well, I can make a different Farfield approximation. New Farfield approximation goes like this. If the field point is sufficiently far away, then these two rays that I'm showing here, this one that goes from the source point to the field point, and this one here that goes from the origin to the field point, are very nearly parallel. We're not saying they're equal in length. We're simply saying that those two rays are parallel if the field point is far enough away. If they're very nearly parallel, then the difference in length is this length. So we can rewrite this expression here, the total distance from the source point to the field point, as the position, the radial position of the field point minus this distance here, right? And this is true in general. It doesn't matter whether the current element's electrically short or not. This dot product here is very simply given in this case, in terms of the coordinate system I've established here, as z prime cosine theta, right? You normally get cosines of angles when you take dot products, and that's what we have here. So now let me exploit this idea. Here's the problem statement. Here's our original phase factor. I can use the approximation I showed on the previous slide to expand the phase factor as follows. And what I get is a spherical wave, which is emanating from the origin, plus, or times I should say, an additional phase factor. And that phase factor is now accounting for the difference in length between the two rays I'm assuming here. This assumes a ray that's emanating from the origin, and then I am making a correction here to account for the change in length because each point along the wire or along the current element is displaced from the origin, and that's the phase factor correction to account for that. So now I make the substitution into the integral. So now the phase factor is as I'm showing here. And as before, I could take anything which is not varying with the variable of integration, z prime, and pull that out. So that has been pulled out, as I've shown here. And this is the new integral. So now if I were to know, if I knew somehow what I z prime was, I would have everything I need to evaluate this integral. Now, let's take a second look at what we just did. We've identified here along the way something that's referred to generally as the Farfield condition. This parallel rays business is really another way of saying this. R is simply greater than 2L squared divided by lambda. This is sometimes known as the Rayleigh distance. That's a historically motivated term. And that's defined as a distance beyond which the error in this parallel rays approximation is less than about 22.5 degrees. Now, that phase error decreases, of course, with increasing distance between the source point or the current distribution and the field point. So typically, this dwindles very quickly to 0. But just being this far out gives us the result that the phase error is less than this. And in practical problems, you find out that really is sufficient to give us an excellent approximation to the actual answer. So now if we summarize here, let's think about everything we've done. First of all, we said that Kr is much greater than 1. The product of the wave number and the distance to the field point, or the distance between the origin and the field point, is much greater than 1. Now, this is another way of saying R is much greater than a wavelength, as I pointed out previously. And what this allowed us to do was to neglect higher order terms in terms of 1 over R. In other words, we got rid of a 1 over R squared term, and that simplified the answer. Another thing we said was that the distance between the origin and the field point was much greater than the length of this current element. And this ensured a 1 over R dependence in magnitude, at least approximately. And then, as I've just identified above, we say that R is R is simply greater than 2L squared divided by lambda. That's the Rayleigh distance. And that tells us that the Farfield phase approximation, this parallel rays approximation, is pretty good. We will require all 3 of these conditions to be true for a field point to be considered in the far field. So if we can show that all 3 of these things are true for a particular field point, then we know that we are in the far field, or at least that's going to be our definition of the far field. And the advantage of knowing that we're in the far field, that we're meeting the far field conditions, is we can invoke these much simpler expressions. Now let me show you how this pays off. So we're going to take a second look at the electrically short electric current element result. So we're going back to the very first problem we did. This was the magnetic vector potential that we obtained in this case. And I'm going to give this a name. I'm just going to call this z hat. I'm going to keep the unit vector, and then just group everything else into this factor a sub z. So the z component of the magnetic vector potential. For the electrically short electric current element, this is the electric field that we obtained. And what we find is that we can write this in terms of the z component of the magnetic vector potential like so. In other words, we didn't really have to take the curl twice, once to get h and then once to get e. We could have gotten e directly from the z component of the magnetic vector potential just by multiplying by j omega times sine theta and knowing what direction the vector was pointing in. Similarly, here is the expression that we previously obtained for h, and we can write this also in terms of the z component of the magnetic vector potential. So in both cases, we have a very, very simple relationship to the radiation integral. In this case, we really didn't have to take the curl twice to get the electric and magnetic fields. As I point out here, it sure would be convenient if we could generalize this so that we could exploit this kind of relationship for other kinds of antennas. If we can generalize this for current distributions in general, then we could always just compute the magnetic vector potential and then use very, very simple expressions to obtain the electric and magnetic fields. Well, here's how we do it. First, we realize that the electric and magnetic fields are transverse to this vector r in the far field. Now remember, r is the vector that points from the origin to the field point. R hat is the direction in which r points, and we know that in the far field, E must be perpendicular to r. How do we know that? Because we know that in the far field, a spherical wave looks very, very much like a uniform plane wave. That's the locally planar approximation. So there's really a very simple way to get the electric field in this case. We take A that we've computed, we subtract off the radial component because we know that E can't have a radial component, and then we just multiply by minus j omega. It's as simple as that. To get H, we just invoke the plane wave relationship. We've already assumed that it's a uniform plane wave, at least locally, so we simply invoke the plane wave relationship to get H from E. Now let me just point out before moving on that we're not saying that we have a plane wave out here. That's absolutely untrue. What we're saying is that if we get far enough away, locally what we have appears to be a uniform plane wave. So globally we have a spherical wave, or a very good approximation to it, but locally we have something which looks like a uniform plane wave, which allows us to invoke these ideas. On your own, what you should do to confirm that this makes sense, you should verify that these relationships give you the expressions on the previous page. In other words, if you now do this, if you now take the known magnetic vector potential for an electrically short electric current element, and you apply these expressions, you get the result that we previously obtained the hard way. That is, by taking the curl twice, once to get H and then again to get E. Okay, so let me now wrap things up. Previously, before we even started this lecture, you hopefully had some idea that to get E and H in general from a current distribution in general, what you did is you integrated over that current distribution to get the magnetic vector potential. You took the curl once to get H, and then you took the curl again to get E. So this is about to get real simple. If we know that our field points satisfy the far field condition, then we now have a new, simpler way to do this in general. The magnetic vector potential looks like this. Note we've invoked the far field conditions to simplify the integral. So we have the spherical phase factor which pops out here, and then this phase factor just represents that correction that emerges from the parallel rays idea. To get E, we just remove the part of A which is radial, and then we multiply by minus j omega w, and then we use the plane wave relationship to get H from E. Let me conclude this lecture by suggesting an exercise. I said some point earlier in the lecture that this use of the Cartesian coordinate system, x, y, and z, was a little bit arbitrary. And it's really easy and somewhat insightful to generalize this, to separate it from the Cartesian coordinate system and come up with a coordinate-free representation. So here's the idea. I'm not going to solve this problem in this lecture, but you should think about it and see if you can come up with this. An electrically short electric current element, I sub e L hat, so I sub e here is some linear distribution of current, show that the electric and magnetic fields in the far field of this current element have the following form. So here's H and here's E. You see no X, Y's, and Z's here. You see simply L hat, which is the direction in which the electric current element is pointing, and then R hat, which is the distance from the origin to the field point. And I claim you can get expressions in this form, and I'm asking you to do that and then find out what these coefficients are, C1 and C2. And I'll just give you an additional hint here. Once you think you've got it, you can do dimensional analysis and make sure that those coefficients are dimensionally consistent. This concludes this lecture on radiation from an electric current element with broader implications, those being the far field condition and the simpler way to compute E and H from a bounded current distribution.